In this video, we're going to explain exactly why the second derivative has anything to do with concavity. Let's jump in. So here you can see that we have an example of a concave up function, at least on a certain interval, and we have a concave down portion of the same function. Now, I think of concave up as being a function that opens up or bends up. So basically, if it looks like a U, it's concave up. And then concave down, I basically think of a function that opens down or bends down. So basically like a downward facing U. So that's how you can remember it. That's what helps me at least. Now, in your class, you probably learned that the first derivative controls whether the function is increasing or decreasing, which I think makes a lot more sense. Because if you have a positive slope, obviously you have to be going up as you go to the right. That's what increasing means. If you have a negative slope, negative first derivative, you have to be going down. Now, I find that this is pretty easy to grasp, but it doesn't make as much sense when you go to concavity, or at least it's not as clear. So what we're trying to answer is why the second derivative has anything to do with this behavior of bending up or bending down. Apparently, a positive second derivative should cause this behavior, where we're bending up, and a negative second derivative should cause this behavior, where we're bending down. But the question is why? So that's what we want to try to answer here. So now let's take a look at a curve that is clearly concave up over the entire interval. In order to understand why the second derivative would be positive here, think about what's happening as we move to the right. Now, as we already talked about, one key thing to understand is that the first derivative is the slope at each point. So right here, no matter which point I go to, whatever the slope of this tangent line is, that is going to be the value of your first derivative. So that usually makes sense. Decreasing to the left, decreasing to the left of 0, increasing to the right of 0. But what we need to understand is the second derivative. And the key here is to understand that the second derivative is not the slope of the function, it is the slope of the slope of the function. In other words, the derivative of the derivative. The second derivative, it's the slope of the tangent line. So just like a positive first derivative means that the y value of the function is increasing, a positive second derivative means that the first derivative of the value of the function is increasing, or the slope of the function is increasing. So I'll just say that again. A positive first derivative means the y value of the function is increasing. A positive second derivative means that the slope of the function is increasing. So think about what that would look like. First off, you can see that as we start off to the left here, we're starting off with a very negative slope. As we go to the right, though, the slope becomes a little bit less negative. In other words, the slope increased. It was a very steep negative number. Now it's a less steep negative number. As I keep going, it's going to get less steep, less negative, more positive, more positive. The slope is increasing until it finally hits 0. And then it's going to keep increasing, actually. Going from 0 to a slightly positive number, and then it's going to get more and more positive. So hopefully it's clear that with this function, as I go from left to right, the slope is becoming more and more positive. In other words, and again, the slope at any given time could be negative or positive. The only requirement for positive concavity or concave up behavior is that it gets more and more positive as you sweep to the right. If that's happening, that is concave up. And hopefully it's clear that if that's happening, it has to produce this upward curvature or this concave up behavior. And now let's look at the concave down situation. Basically, it's the same thing. You can just reverse the behavior. As we start off with a function that's clearly concave down or open down throughout the entirety of the interval, or actually negative infinity to infinity, if you want to think of it like that. Basically, if we start to the left, we're starting off with very, very positive slopes. And as we go to the right, as we move to the right, the slopes are getting more and more negative now. Again, they're still positive, they're just more negative than they used to be. So they're getting more negative, more negative. The slope is going down, if you want to think of it like that. So the slope is going down, it hits 0. Slope is still going down, and then as we keep moving to the right, they just get more and more steep in the negative direction. So the key pattern here is that the slope, as we sweep to the right, the slope keeps getting more negative every time we go to the right from where it started. That is why this looks like concave down behavior or downward bending behavior. If the slope keeps getting more negative, that'll cause you to bend down. If the slope keeps getting more positive, that'll cause you to bend up. So there you go. Hopefully now it makes more sense why the second derivative has to do with this concavity in this curvature. It's really just measuring the slope of the slope. If you have any questions, feel free to post in the comments. Otherwise, I will catch you next time. See you.